Okay, so here's our last topic. We're going to talk about two terms. We're going to talk about thermodynamics and efficiency. And this last topic is kind of my my leftovers bit. I don't know whether this analogy makes no sense at all or not, but sometimes my family on Sunday nights, we have to like clean out the fridge of all the food that's been eaten over the week. And rather than make a new meal on Sundays, we just we eat all the leftovers. I don't know if anybody else does this. So someone's having pizza, someone's having that last hamburger, someone's having, a little bit of soup that's left in the fridge. Does that make sense at all? That's kind of what this topic here is. This is the leftovers bit. So this is all of the random little topics that weren't really big enough to make an entire lesson about. Kind of just throwing them all together here at the end. So I got to be honest, if today's lesson feels a little bit disjointed, that is kind of the point here. I'm just throwing all the leftover random bits together in one big topic. Fair enough? So we're going to talk a bit about thermodynamics. We're going to talk a bit about efficiency, and I probably could have added to this. We're also going to talk about some engines as well. There's an outcome in physics that you're supposed to learn about how an engine works. I really couldn't find a better spot to put that, so I just kind of threw it at the end and just said, here's a leftovers day. So anyways, let's go. So the first thing we want to talk about is thermodynamics, and I want to talk about the idea of machines. That's kind of where we're going to go a bit today. Imagine that you had a machine, like say a car. Okay, our cars are powered with gasoline, but a lot of times we lose energy. I want to use the word lose though in brackets. Ideally, all of the energy that we begin with, we should end with. You guys remember this formula from yesterday or last day where we had gravitational energy and it turned into kinetic energy? As somebody on top of a cliff or a building or something drops an object, ideally all of the potential energy up here should turn into kinetic. What system would that require though? You guys remember the systems we talked about? What system? What'd you say? Yeah, we need an isolated system. An isolated system is one where there's no loss of energy, like a thermos. A thermos in theory should prevent loss of energy. Well, that's really not true though, right? Imagine that you had nice hot soup in your thermos that mom packed you for lunch. Maybe by lunchtime it's still warm, right? But what if it was 8 days later? Is it still going to be warm 8 days later? Or 2 years after that? Well, first of all, it'd be gross, right? But the point I'm trying to get at here is that all systems are probably going to lose energy over time, often due to heat. And a car, which is where I started this thought, is a good example of that. What is a car supposed to do for energy? What sort of energy do you want a car producing? What is the goal of a car? Movement. The energy of movement is known as kinetic. So a car wants kinetic energy, but 33% of it gets wasted on heat. Right? There's actually cooling systems in your car meant to remove that excess heat. So as much as we would like to have 100% efficiency, which is what we're going to get to as well, that's really not the case. We're going to lose energy over time. Okay. So here's the first law I need you guys to know. And maybe highlight this or write this down because I am going to assess you on whether or not you know the two laws of thermodynamics. There are two of them. Okay. I'm going to give you the technical definitions, and then I'm going to give you some analogies, and hopefully the analogies will help kind of make sense as well. So here's the first one. First law of thermodynamics says that the total amount of energy, including heat, must remain constant. What that basically means is, like this picture has, whatever energy you start with, it better be the same as the energy afterwards. Another way of putting it is that you cannot get more energy. Whatever you start with is what you're finishing with. I can't start with 10 joules and somehow make 11 or 12 or 13. Okay. Here's the analogy I want to use. It's a gambling analogy. I hope that's okay. You guys know Vegas? The idea of going into Vegas is that you want to go make some money there, right? But the house always wins is a phrase they use in Vegas, where it's although you might win, the reason why Vegas makes so much money is that the rules are stacked in their favor. Okay, if I want to use a gambling analogy for the first law of thermodynamics, it basically means that you can't come out ahead. If you went into Vegas with $100, the best you could hope for is to get your 100 back. You're not going to make 200 or 300. Okay, that's how energy works. Whatever energy you begin with, the best you could hope for is to just get back your return. You're not going to all of a sudden magically make more energy. Okay, let me use this example again here. Let's say that Brady's on the roof dropping a volleyball off of it, and there's 100 joules of energy up here. There is no way that after this ball falls all the way down to the ground, that there's now going to be 200 joules of energy down here. Does that make sense? Like, that's just not possible. Okay. A classic example of this, maybe you've even seen this video, is a pendulum. If you have a pendulum, like basically a ball on a string, there was once a physicist at MIT, he did this famous video where he took the ball right here, put it right next to his chin, it was a bowling ball, and he let it go. And it swung all the way to the other side, and it swung all the way back, and he just stood there, and it landed like this far away from him. Anyone ever seen that YouTube video? Yeah, some of you have seen that one, right? That is a good illustration of the first law of thermodynamics, which he knew that however much energy the ball had right here, I'll call it E1, as it swung all the way there and swung all the way back at E2, it couldn't somehow have more. So it's not like the ball was going to all of a sudden go all the way there, come back, and then come up higher and smack him in the face. Does that make sense? That's the first law. So basically, in people words, you cannot get more energy than you begin with. Whatever you start with, that's the best you can hope to have. Okay. And the second concept I want to talk about is, before I get to that, I want to talk about like a hypothetical idea. Maybe you've heard of this before. It's called a perpetual motion machine. Scientists in like the 1800s, they were always trying to devise one of these, where ideally what would happen is this machine would run for forever. Somehow you'd like set it off, and it would keep going, like this picture right here. Imagine that you had like water falling out of the bottom right here, and like it somehow managed to go all the way back up to the top, and it would just keep going for forever. That's not possible, because not only can you not get more energy than you start with, we're always going to quote unquote lose energy. We always lose a little bit due to things like friction or heat or sound, right? It's always a little bit less than you started with. Let me go back to this picture right here. The guy who did the whole bowling ball across the stage on the string all the way there and back, why did the bowling ball not quite even make it back to the original spot? Why was it just slightly less than before? Friction, right? The bowling ball, as it was going through the air, it was hitting particles of air. Not a lot, but enough to slow it down just a little bit, just with wind resistance. Right? So what ends up happening is the ball would come from here with, let's say 12 meters per second at speed, and it goes all the way there, and it comes all the way back, and now it's going 11.9 meters per second. Why did it lose some speed? Friction, air resistance. The fact that it's not truly an isolated system. How is that similar to our lab with Hot Wheels? Isn't that the reason why our Hot Wheels eventually slowed down? Is that bumping into the sides and air resistance and friction of the wheels on the ground, right? Wasn't that going to eventually cause a quote-unquote loss of energy? Okay. So that leads to the second law of thermodynamics. Now, the technical jargon is this. It says that heat naturally flows from a hot object to a cold one, never from cold to hot. That's the technical jargon. Here's what it means, though. It means that you're always going to lose at least some energy on like an off-ramp. Okay? Imagine that you want some energy to go from here to here. Ideally, if you start with 100% right here, we would love to have 100% right here. That's ideally what would happen. Since we already know that we can't get 103%, it will never be above what we started with. But that's not actually true. Chances are it's going to be something more like 60% right here, because you're going to have lost some heat, because heat always flows from hot things to cold things. There's always going to be like a loss. Now these two numbers right here, they should add up to 100. It's going to be in like an uncapturable form. Let me give you an example here. These light bulbs. What's the goal of the light bulbs in the classroom? To give off light. But some of them aren't very efficient. We've gotten better at building more efficient machines, especially in the last 10 years. But like chances are our light bulbs are doing something more like this. Ideally, we'd like all of the electricity to turn into light, but maybe only 98% of it turns into light. You began with electricity, and electricity is supposed to give you light. But what do these light bulbs also produce? Heat. And if you listen really carefully, sometimes they even produce sound. So maybe 2% of the energy is quote-unquote lost. because it's being converted into like unuseful forms of energy. Okay. That's the second law of thermodynamics. Because things always flow from hot to cold, energy becomes lost over time. So here's the analogy of that in terms of gambling then. First law of thermodynamics basically says you cannot come out ahead. If you're trying to gamble, the best you can hope for is to get back what you put in. You're not going to make money against Vegas. Second law of thermodynamics says not only will you not come out ahead, you're guaranteed to lose at least something. Okay. And so those are basically the two rules we know of energy, is that as energy changes forms, it is not perfectly efficient, which is kind of the next topic I've got here. Now, some kids may argue, but hang on, can't heat move from cold to hot? What about a refrigerator or an air conditioner? Doesn't that pump out cold air? Well, kind of, but let's discuss how like a air conditioner actually works, or a freezer actually works here. Okay. In order for you to get cold air coming out of the vents in your air conditioning system, like this out here is cold air. But what do you require in order to get cold air coming out of these vents right here? There's this little tube right here. Now this looks differently depending on what your air conditioning unit looks like, but like it basically has to shoot the hot air outside of the house. Okay. Maybe your air conditioner unit doesn't look like this, but if you have like one of those big industrial ones that's like a big, I don't know, cube-looking box with a fan in the middle of it on the outside of your house, what is that thing doing? It is literally pushing the hot air out of your house. And if you push the hot air out of your house, what are you left with? Cold air. Okay. So, I mean, if you're going to argue that heat can go from cold to hot, the only way that works is if you're doing work by like using this pump to do that. Okay. Your refrigerator or freezer, the inside of the refrigerator or freezer, yes, it is cold, but if you feel like the back of it, yeah, it's quite warm. Because really what's ended up happening is you just push the hot air out, that's all. Okay. Okay, so let's move on to like the next topic of our leftovers today. I need you guys to know this last formula. This is the last one on our list. It's the efficiency formula. And you've probably seen this somehow before. It's exactly how we calculate a percentage. You know how like you calculate your mark on something? Let's say that you got a score of 8 out of 10 on a quiz. 8 out of 10 means that you got 80%, right? Well, we can do the exact same thing to calculate efficiency, only now we're going to do it with energy. The formula basically says, tell me how much useful output did you actually get, and then divide by how much input there was available. And then when you want to, just times it by 100 to make it a percentage. Let me give you an example. Let's say that our light bulbs produced 98 joules of energy. However, let's say that it could have produced as much as 100 joules of energy. Well, 98 out of 100 means that it is a 98% efficient device. All you've got to do basically is imagine this picture right here. If you start with 100 of something and only 98 of it is useful, well then just divide these two numbers by each other, divide these two numbers, now you have an efficiency. It's actually a really easy formula to work with. So, brief side question, why does efficiency matter? Why do we care? Well, nowadays it's all about money. If you go buy, say, like new appliances or vehicles, we're always looking for high efficiency ones. I just had to buy a washing machine recently, and I mean, it comes with all of these new like high efficiency labels. It tells me just how much money a year I'm going to spend using this, right? Even light bulbs. Do you guys know how like in the last 15 or 10 years we've actually changed our light bulb style? They used to be like those ones that are like the round bulb, and there's a little filament in the middle, and it gives off a lot of heat. And now we use these newer ones here, these fluorescent ones instead, rather than the incandescent light bulbs. They've changed those. Cars are another good example. We're trying to make cars that are more efficient so that we don't waste so much money on gas. And I mean, not only is it about money, but it's also about maybe saving the environment. But in general, we like efficient things, right? Efficiency is good for saving money. So let's try an example. Let's say that a crane is capable of inputting 2.3 times 10 to the 4 joules of energy. And when it's done, its output is only 8 times 10 to the 3 joules. Why was there like a loss of energy? Why are these two numbers not the same as each other? What is energy being lost to? Heat, sound, friction, something along those lines, right? Air resistance, right? There really is no such thing as a perfect system. You're going to lose some energy due to these sort of things. Heat, light, sound, air resistance, right? So all we got to do is figure out the efficiency. So just like you would on, say, like a test, what is the most you could have earned? Most possible. Well, the bigger number is the most you could have earned would have been 2.30 times 10 to the 4 joules. That's the most you could have earned. Okay. And on the top of the fraction, the question is then, like, what did you get? And in this particular equation right here, it got 8.00 times 10 to the 3 joules. So you got 8,000 basically out of 23,000. All you gotta do is just divide them times by 100. Okay, I gotta grab my calculator. I'm just gonna sit next to you for a second here. So, I mean, I'm even gonna change the way I write this number. This number right here, 8.00 times 10 to the 3, is really the number 8,000. And this number right here is really the number 23,000. So all I've got to do is just divide the two of them. 8,000 out of 23,000 times by 100 to make it a percent. Apparently the crane is only 34.8% efficient. Okay. So this is one of the easier formulas I think we have to work with. All you've got to do is just divide two numbers by each other and make it a percentage. Can this percentage be over 100? What law does that break if it were somehow over 100? The first or the second law? The first law. First law of thermodynamics basically says you cannot have a machine that is more than 100% efficient. Okay. Secondly, would we ever actually expect a 100% efficient machine? That would be lovely. But unfortunately, it just does not seem to work that way. If it did, by the way, that's called a perpetual motion machine. That would be great. I mean, something would literally run for forever, but that doesn't even work. And so not only will this percentage never be 100%, I guarantee you it's less than 100%. And that's due to the second law of thermodynamics, which basically states that you're always going to lose energy because heat always goes from hot things to cold things. There is no such thing as a truly isolated system. It would be lovely if there was, but even energy is still going to travel from one place to another. Did that make sense? You guys able to follow along on this math example here? Okay, let's try one more example. Let's go backwards this time. I'm going to tell you that an internal combustion engine is only 15% efficient. I'm going to tell you that its input energy is 32,000 joules. How much work can it do? There's a bit of a twist on this one here. Rather than me telling you what the two numbers are and you're getting me a percentage, now it looks more like this. You had 15%. I want to know how much work can be done if 32,000 of joules of energy is the most you can have. This is the most you can have. This 32,000 number right here, it's 15% efficient. I just got to figure out how much was actually done. Will this number that we end up with, will it be bigger or smaller than 32,000? Will the answer we get, like here, bigger or smaller than 32,000? Much smaller. How much smaller? 15% smaller, right? All you basically got to do math-wise is take 32,000 joules and times it by 15%. The point I want to make right here, though, is you don't times by the number 15. If you were to take 32,000 and times by 15, you're going to get a much bigger number, and that's wrong. You shouldn't times by 15, you should times by 0.15. You guys know how to convert a decimal back to a percentage kind of thing there? All right, so take 32,000 and times by 0.15, and you actually get this number here. Hopefully you get what I got. It's 4,800 joules. which kind of makes sense, right? Because isn't 4,800 out of 3,200? Wouldn't that give you about 15%? So we just need to do the right number of sig digs. So this had 3 sig digs, this had 3 sig digs. So when I'm done, let's call this 4.80. One more sig dig. Can one of you guys close the door to the classroom? Sorry, it's just kind of loud out there. There, let's do this. 4.80, thank you by the way. 4.80 E3. See how I moved the decimal place over 1, 2, 3 times? There's a good way of writing it. Or you could even write 4.80 kilojoules. Because you know how a 10 to the 3 is a kilo of something? 1,000 of something is a kilo. So either of those will work. This is probably not the hardest formula we have. All you have to do is divide 2 numbers by each other. Or if I give you the percentage, just make sure you times by the decimal number version of it. Don't times by 15 itself. Because otherwise you would get a bigger number, and that breaks the first law because you can't get more than you started with. That's all. I'm going to go back to this slide right here. I don't know whether you guys need to write this one down on your formula sheet, but if you want a second here, write this formula down on your sheet. Don't forget to times by 100, though. For some reason, I don't have that written here. It's always your output over your input times by 100. Honestly, it's the exact same way that you calculate a mark on a test, though, right? You just divide 2 numbers by each other. Does anybody have any questions on this? Yeah, this will be on our last quiz. Is it something that you kind of already knew, though, perhaps? Maybe not the terminology, but, like, you probably knew that efficiency is good. You probably knew that, like, you don't just get free energy from nowhere. It has to come from somewhere. And, you always lose a little bit in the process. There was even that test question on our last quiz where I think I gave you, like, 30 joules of energy, and then you finished with 29 joules of energy. And you had to, like, subtract the 2 numbers and figure out how much energy was lost. I think it was the last quiz question. Hopefully that kind of makes sense, the idea that you're never going to truly have an isolated system. Okay, here's my second part of like some random leftovers bit. I always leave this till last because I think this part is dumb. But I'm supposed to teach it to you, and I'm going to tell you right now, I'm only going to put 1 test question on this. So don't stress over this too much. I'll even tell you the test question if you want later. But we're supposed to talk about engines. It's an outcome we need to know. So I'm going to go through the history of engine development, and that's kind of our last little topic. But yeah, this is kind of like, this is one of those like random leftover bits where it's like, this doesn't even really fit in all that well, but it's in the curriculum. So you guys are supposed to know about how engines were developed. So here's some history, some pictures. There was a guy named Hero. He's like one of those ancient Greeks, and he made what we now know is one of the first engines ever discovered. Although he really built it as a toy. Here's the picture, basically. He built a fire underneath this dish of water right here, and it caused some steam to rise. And as the steam was rising, it would push this side, so that the steam right here would cause this ball to rotate like this. And as it rotated this way, well, then this side could pick up the steam, and it would push it that way. And basically, it started to rotate. It was basically a toy. He just figured out how to make something spin using steam and fire. And so my notes are here. It didn't actually serve any practical purpose. He caused it to spin. It's like the world's first fidget spinner, I guess. Toy ball that spun. Okay. Later a guy, now I always forget how to say his name. It's a Dutch scientist. I think it's Huygens, but I might be saying it wrong. He made an engine. His engine, though, was a little bit more dangerous. What he basically did is he made a piston. And this right here is a piston. It's basically an object that can go up and down. On this end right here, there's a weight. Okay? And imagine that he wants to get this weight to either move up or down. What he did, basically, is he caused this thing right here. There's a little plunger inside here. to move by setting off an explosion. Okay, imagine that right inside here, you blew something up with an explosion. Okay, that's why you can see steam coming out of here. If you were to blow something up with an explosion, it could actually maybe cause this thing to go. I need a new color here. Hang on. It can maybe cause this thing to go flying downwards because you're literally setting off an explosion inside here, and this thing goes flying one direction, right? Well, this thing's attached to a rope. So when this thing goes all the way down to here, the rope comes with it. What happens to this box right here? Maybe it lifts it back up again, right? And so that's kind of the idea. But this was a problem here. You basically had to set off explosions after explosions over and over again. And not only was it dangerous, but it basically, like, the parts that he had eventually started to break because he was literally setting off bombs all the time. So when the piston moves back down, it lifted up a weight. Right? When this piston goes down, this weight goes up. But you literally had to, like, explode. He used gunpowder. Okay? So maybe an engine, but really not the kind of steam engine you're used to. It's definitely not the engine that we use in our cars right now. This is the first steam engine. It was discovered by a guy named Thomas Savery. We're talking like hundreds of years ago now. And let me see if I can try to describe how this worked. It's all about pressure. Okay. If you know a little bit about how pressure works and vacuums work in terms of like negative pressure can cause something to get like sucked in, that's basically what happened here. He boiled some water in this pot right here, and all these X's, by the way, are valves that are closed or open. So he heats up some steam right here, and then he opens up this valve. And as he opens up this valve, all of the steam goes rushing from here to here, and when there's steam inside of here, it then pushes down on this water. Let me say that again, just to make sure you catch this. He heats up this vat of water right here. Both of these two things are closed. And this vat starts to make steam. New color. You can see it better. Steam. And the steam is building up pressure, and it wants to go through this little valve right here, but the valve's closed. Eventually, you open the valve. Well, where does the steam go? The steam goes into here. And there's so much steam and so much pressure that it pushes down on this water. Does that make sense? Now, that creates more pressure, and now there's two valves right here. And basically, depending on which valves you open, if you were to then open this valve right here, all of a sudden that pressure is going to push up here, and it's going to push water through the pipe. Now, eventually, you're going to maybe run out of water there, though, right? So maybe you close this valve, and now you want to open this valve here instead. And if you can find a way to create some negative pressure, you've ever heard of that term before there? Where there's kind of like a lack of pressure in here, probably by cooling this back down again using valve C, you can actually draw water up the tube, kind of like a straw. You guys know how you can like suck water up a straw? That's basically what's happening here by using negative pressure. And so now this was very costly to operate. It was very inefficient. And the reason why is that you had to have all of these different valves that literally a person would have to turn open and closed. But what you could do is you could pump water out of the ground up to the top right here, which is kind of useful. I mean, other than that, then you'd have to like carry it up in buckets. That was going to take a long time. So, fast forward a few years, a guy named Newcomen builds an engine, and here's the biggest difference. You don't have to manually open all of these valves. He found a way to basically make the system open all the valves for you. But the problem was it wore out quickly due to heating and cooling. And I'm going to try to explain this engine to you using 3 pictures on the next slide. So I'm going to come back to this one right here, but let's look at these pictures here. Okay. Basically what happens is this thing right here, it is going to tip back and forth. It's going to go like up like this, and then it's going to go back. It's going to rock back and forth like a rocking horse. Okay. The question is, how do you get it to rock back and forth like a rocking horse? Okay. So right here, there's a piston. Can you guys see all of this red inside of here? Okay. Let's imagine that that's again some sort of steam. And what we've done is we've set off a small explosion by heating this up, and it causes the piston to get pushed down. Okay. So by pushing this piston down, by setting off an explosion, just like the Huygens kind of gunpowder concept, what ends up happening is if this goes down, this goes down. But if this side goes down, this side right here goes up. that make sense? And with this side right here going up, what ended up happening is it pulls this plunger up right here. It causes negative pressure, and you can cause this water right here to come out of this vat right here. Okay. However, the problem is once this goes down and this goes back up, well, that's done once. How do we get it to go back to its initial position again? And so what ends up happening is you then set off an explosion on the bottom side of the piston. Well, when you set off an explosion on the bottom side of the piston, it now pushes it back up again. Does that make sense? So you explode something on this side right here, pushes the piston down. Then you explode something on the opposite side, push it back up again. And this thing right here would have been like a coolant system. And its job is basically to cool it back down again, because it's basically going hot, cold, hot, cold, hot, cold, hot, cold. And you're pushing back and forth with a series of it wasn't actually explosions though, it would have been steam again. Okay. Huygens, he used actual gunpowder, but these guys right here, they were using steam by boiling water to do it. So this thing right here would have probably been something that boiled the water. And you can see the pipes right here. The pipes could go up to the top, causing steam to push down, or the pipes could go through the bottom, causing steam to go up. So kind of a clever little engine used to basically suck water out over here, but not very efficient. Okay. James Watt created the steam engine, the double-acting steam engine, and it's very similar as well. And what really was useful about Watt's engine is that this allowed you to start turning a wheel with it. Okay. This is really the first time that we decided to make an engine that you could somehow have something go around in a circle and provide constant motion to, in this little thing right here. Let me try to explain the concept behind Watt's engine. It's very similar, but with a clever design. I've got more pictures to describe this. What you've got right here is this little piece. This piece right here is the key to everything. See how there's two little blocking pieces right here and right here? See that right here and right here? As this thing moves, it's going to cover some holes, and it's going to deflect where steam ends up going. Currently, what ends up happening is this is causing steam to go from here through this pathway right here. Okay. However, as this piece moves, watch how this little piece right here has been moved over to the further location. Well, now what ends up happening is now when something comes through here, it actually goes back through a secondary loop. And as this piece goes back and forth and back and forth, it changes which loop is open. So when it's on this side right here, the far loop is open. And when it gets pushed this way, the close loop is open. Okay. Now let's describe what's happening with steam this whole time. Okay. What ends up happening right here is that there's kind of an input of steam right here. And the steam is able to go through the open section into here, and as steam builds up pressure, it wants to push the plunger this way. And what ends up happening is by pushing it this way, all of this blue gas right here, it gets pushed through that vent and out the exhaust system. Okay. But what ends up happening is because this thing is hooked up to some sort of turntable, as this thing gets pushed this way, it ends up causing it to eventually, through a process, push this guy the other way. So by pushing this thing towards our left, it causes this guy to get pushed towards the right, and eventually what happens is, this thing's been pushed all the way this way now, and all of our gas has now been exhausted out. But then this thing's got pushed to the second location. This is location 1. This is now location 2. Now this thing has pushed the close vent over here. And what ends up happening now is, now the steam, rather than coming in through this side over here, now it can come in through the opposite direction. And it pushes the vent back this way. And as it pushes it back this way, all of this red steam that had filled up this container right here, it gets pushed back out the other way. And what ends up happening is now this thing goes back this way. But hang on, if this thing goes back this way, this one's going to follow it. And so if this one follows it, then this little lever right here moves back and forth and back and forth. And basically what ends up happening is it's a double action piston, which is what I have right here. And so it was a really clever design. And the long and short of it is that now it can start turning a wheel because it kept going back and forth naturally on its own. All you had to do is just keep pumping hot steam in through here. And it would go into here. It would push this thing that way. All of the blue would get pushed out. It would cause this thing to get pushed to its new location, location 2. So now it's full right here. Steam wants to come in here. But now this thing gets pushed to location 2. It's now sitting over here. Now the steam comes in through this way, pushes it back. The steam that just came in through here that was red is now blue, gets pushed back out like this. And eventually, this thing gets pulled back to location 1, and it just repeats itself. Okay, last topic, last kind of idea. Again, I'm only going to test you on this with one question, because it's sort of a random bit to have to teach you about. You need to know about the internal combustion engine, which is basically what we use in our cars right now. And it's basically, it's a very similar process to Watt's steam engine, only what we end up having is multiple pistons firing at the same time. Okay. The idea is that we burn a fuel, so rather than using steam, we burn fuel. And there's basically 4 different stages that a piston could be in. And I've got a bunch of pictures describing them. There's what's known as the intake, compression, power, and exhaust strokes. And I've got one slide for each. Okay, so here's the intake stroke. A piston, what it should do is it's supposed to go up and down and rotate in kind of a circle, kind of like some of the pictures you've seen before. On the intake stroke, what ends up happening is one of these sides opens up and it puts some gasoline in. Okay. So the valve opens, the piston moves downwards, and we draw air and gas into the cylinder. So this thing is going to go down, and this whole area is going to fill with air and gas. And that's what's going to happen right here. However, because it's swinging all the way around in a circle, it's now filled with air and gas, but now it's pushed its way back up again. And so it's very compressed. So on the way down, you can kind of imagine this piston going down. When it's down at its lowest stage right here, you pumped in a whole bunch of air and gas. And as it swings around in a circle, it's going to come back and it's going to compress all of that air and gas into the smallest section possible. And these little valves right here are now closed. The intake valve and the exhaust valve are now closed. You've got a really, really, really small compressed area. And there is a spark plug. What does a spark plug do? Provides a spark, right? And what should happen then is we're going to light this gas on fire. And it is going to literally explode, which is what we've got in this next picture. This is now called the power stroke. The spark plug goes off. This now explodes. And well, what is the piston going to naturally want to do? It's going to want to go down, right? And so it causes this piston to really forcefully get pushed downwards. Right? Well, it's going to get pushed down, but it's going to swing around in a circle and come right back up again. So when it comes right back up again, we need to have one more thing ready. We need to have the exhaust stroke. Because we've got to push out all of the old products. We've got to push them out of the exhaust valve so that we can start over new again by having the opening valve allow new stuff to come in. So after it's exploded, it's got to push everything out this one right here so that we can restart on the intake valve by closing the exhaust valve and re-bringing in air and gas. So those are the 4 strokes basically in a piston. And I have some notes here. Most internal combustion engines either have 4, 6, or 8 pistons. You might recognize this if you know anything about vehicles. Like, for example, this is a V4, a V6, or a V8 engine. It basically lets you know how many pistons there are firing in your car. The more that there are, the stronger your engine is working. Okay. So many of them have 6, but a V8 would have 8 pistons all firing, and they'd be at different times. You always want to have a piston so that always one of them is in the power stroke. That way, always at any given moment, one of these pistons has an explosion. It could be this one, then it's this one, then it's this one, then it's this one. Now back to you, right? And the idea is that at any given moment, always one of the pistons in your car is undergoing the small explosion with the spark plug, so that always one of them is getting pushed down. Okay, so here's kind of one last picture, and then we'll call her quits for the day. This now illustrates the 4 different sections of where a vehicle could be. Which one of these ones is undergoing the power stroke currently? Could you guys identify that? Which one is about to explode? It's this one over here. Does that make sense? Like here, the spark plug is going off. This guy is about to undergo the power stroke. Okay. Could you tell me which one is about to undergo the exhaust stroke? Which one is finished the power and is now pushing everything out? The very, very first one. You can see how this one right here, how it's going to start trying to release right here. Ideally, we're going to start trying to release things right here. Which one would be the intake? Oh, sorry, I take that back. That's not right. It would be... Actually, I really can't tell what the difference between these two right here. One of these right here is probably exhaust. It's probably this one here. This one's probably exhaust. Because what's happening is all of this right here is getting pushed out. And this one is probably the intake one, where we're bringing stuff in. And then finally, this one right here should be the compression one, where everything's been compressed up as much as it possibly can be, waiting for it to explode. So I actually can't tell which one is which. I'm assuming the gray stuff is the exhaust. We're shooting the exhaust out. And then here we're bringing the intake in. So this one's not really clear. Hopefully that makes sense at all. I am not putting this on much of your assessments. I believe I'm putting one question on your test on it. I'll even tell you what to study sometime later, so don't stress out over engines. But hopefully you now have a better idea of how an engine works. That's useful. So, okay, that was my leftovers day. So we talked about three things. We talked about engines, which is kind of random, but hopefully you know a little bit more about how an engine works now. Hopefully you can kind of visualize it. I had a lot of pictures. Hopefully I described it well. Two, we talked about laws of thermodynamics. There's two of them I need you to know. First law basically says you can't get more energy than you start with. Second law says not only can you not get ahead and make more than you start with, I guarantee you're losing something. There's always going to be a little bit of loss of energy because there's no such thing as a truly isolated system. And then finally we talked about a formula. The efficiency formula is basically just divide two numbers by each other. Take 7 and divide it by 9. There, that's your percentage. 7 over 9 times 100. So, guys, that's it. I've taught you everything you need to know for physics. So here's where we go from here. We've got like 15 minutes left. Today, I've got a little bit of work time. Tomorrow we're going to watch a YouTube or watch a video. Wednesday, I've got a work day for you. And then Thursday, we're going to try our practice unit test. Okay? If you haven't gone over your last quiz with me, you really should. If you haven't been working on your assignment over the last little while, you really should. Same thing with your labs. Do all of these activities to help build our skills, and then, yeah, we'll try our practice unit test Thursday. Sound good? Okay, there's 15 minutes left here, so you guys are free to go somewhere if you want, or find me and ask questions, okay?